Hey Srini, good
Hey,
morning.
Aaron. Good morning. Sorry, I was late.
Yeah, good. You were not available yesterday, I believe.
Yeah, yesterday I had some work, so I couldn't
Uh,
able to attend the call.
yeah, no worries.
I'll
I
go through the
I
recording.
remember because we were discussing very important topic yesterday, so I was checking. Everybody it was very important session. We started with uh, the internals, Spark internals. So we had a
Okay,
session. Um, we will continue, but please go through the yesterday's video
sure.
recording. It is very important. Basically, we have covered very important foundation topics yesterday with these Spark internals. Okay. All right. So what we will do today, I will quickly um, recap what we have done yesterday, uh, and then we will move on to the um, topics that we talked about. One is the join strategies, Spark join strategies, and then the cache. And what else? We thought of three topics yesterday. One was cache, one was join strategies. What else? I will check. I don't know what is. Okay. Yeah, we'll talk about it. So anybody wants to recap yesterday? What is DAG? Let me share my screen. Then I will ask somebody to take a look at it. Okay. So who can talk about this?
So
What's happening? Uh,
DAG is a directional acyclic graph. It
mhm,
represents how the flow of the spark jobs happen.
mhm.
Uh, and
Okay, good. Anybody else want to add what these we are seeing here? One, two, three, four, five, six.
There is like a exchange when we
Of stages,
transformation
right? Different stages
with
of the
different
job.
stages. Yeah, new stage will create and uh, exchange stage and one more thing is that
Yeah.
we
New
told that
stage is
important.
created when there is an exchange. What does exchange mean? Exchange means data is exchanging, which is shuffle,
Yeah, shuffle. Yeah,
called data
yes,
shuffle. So when
yes.
there is a shuffle, it's called represented as exchange. Then then there is a new stage that is created, right?
Exchange in sense means when you're running in the Spark means it's a data is streaming means like when processing or anything means it will shift into multiple create multiple stages.
Now, so we talked about that briefly yesterday. Exchange, data exchange means it's shuffling. Like here, what we mean by that is if we have a chunk of data which is
Okay.
into multiple partitions, that's what we
Uh-huh.
called about distributed computing or parallel processing.
Okay.
So each partition may be on a different machine. Each machine can have multiple partitions.
Mhm.
Now, instead of processing everything at one place, now the data is split into multiple partitions in multiple machines.
machines.
If I want to join or co-locate the similar data, then I have to get the data with similar keys onto it to one place. So that is called shuffling here. So here, if I see, I'm counting the frequency of words. River is here, river is here. Okay, deer is here and deer is here. But I want to get all deers into one. So this deer is from here. We are doing a shuffling. Okay, so deer from here we are shuffling, moving it here. and the deer from here, we are moving here. So both the deers are at one place. Now I can simply count how many are there here and say deer is 2. So that is the final result. So this is called map and this is called reducing. Between map and reduce, there is a process called shuffling. This is the age-old algorithm where, if you, it's very simple concept in our daily life, what we do. For example, when we go to any vegetable market, sometimes everything gets mixed up, get all the vegetables. When we come home, we dump everything, then we start starting, right? Buy vegetables, eat vegetables separately, and then take that and put it separately. So similar things, we split the data into partitions, we process on individual data, something like this.
How many exchanges happened in the previous example you showed? Like,
Yeah.
how many exchanges happened? How
This is
many stages created?
this is only one exchange.
Okay, so
It's not
got it.
like how many, it's not like each partition will have one exchange or each element will have one exchange. Each stage will have one exchange. Here, the data is being shuffled from this data frame, having
One
multiple
shuffling is
partitions.
called one exchange.
Huh?
One shuffling is called one exchange. We can
Yeah,
remind.
whenever
We can,
there can be, yeah, basically you can say that each exchange is a shuffle.
each
Data
exchange.
shuffling. If we look at this also, when we want to just sum up all of these, right? So instead of doing sequentially, we split on multiple partitions on different workers. This is the master. These are different workers. So each worker gets some records. We are distributing the work. They get total their whatever data they have, and then they send it. So this worker will send, I have, my total is 450, worker 2 will get 650, worker 3 will get 300, just like the election. When you do the counting of the votes from each EVM, you get some count. So each worker is giving their own count for those workers. It can be, again, depending on groups also. So once we get that, master will collect everything and then total everything and then give you the total. So this is kind of the Spark architecture we talked about, master and workers. That is
one thing, Harun, means this is a just for simple seeing this example. Okay, this is example we manually defining this one. Suppose it's a huge volume of data. Means and multiple dimensions or multiple metrics. How Spark can decide what to do what? Means suppose I have five dimensions and 5 metrics. Means how will Spark decide how to split this data? Is there any certain criteria to it can decide how we can do shuffling or how we can do map?
Yeah. So basically, it's called partitions. The moment you read the data, there is a default partition level that you can set. So default, it gets to 200 partitions. It depends on how many machines you have, how many workers you have. That also we talked about yesterday. How many executors we have, how much parallel processing you can do. Based on that, you can define your number of partitions. So default, you get 200. Then you can do repartition. So you can change from 200 if you want to go to 400 or 500, or you can coalesce. Coalesces, you can reduce the partitions. You say, I have very less data, but there are too many empty partitions. The jobs are just triggering, doing nothing because the partitions are empty. There is nothing to do. So we coalesce, we reduce the number of partitions from 200 to say 10 partitions. So then the jobs will run, the tasks will run. The number of tasks will be 10. So number of tasks are always equal to number of partitions you have. So it will run 10 tasks and then spit out 10 files to write to the disk or write to the files that you're, when you're doing the operation data frame dot write. So that is the shuffling. You can control how many partitions you want, but how do you actually do control the shuffling? Is by avoiding as much as possible the joins or white transformations. So wherever there is aggregate group by key. So when you say group by, all the data that is related to the similar key has to be coexisting at one place. So that's when you do group by, there is always data shuffling. When you do repartition, there is data shuffling. So you have to identify where the shuffling is happening, and this is your kind of mark. Wherever there is a shuffling, it's a bottleneck for performance. Of course, you cannot avoid completely. This is where majority of the resources are utilized, right? Like network, IO, memory, right? All of that, because we are hauling the data around the network. So to do that, you can use some techniques like sorting. You can do pre-sorting when you are processing. When you're selecting the data itself, you can sort and then bring in the data so that the shuffling is reduced, right? And then the sorting is done on the database or on the machine. However, if you use Delta, it's again still Spark only. So that does computing. So basically, yeah, you do have control on how many partitions you want, how you want to distribute the data. But as I was also talking yesterday, most of the complexity is now taken out. It's managed by the platform, right? So now this is where we talked about the scaling. When you are doing the creating a compute, you said how many workers I want, what is the configuration of that worker, 16 GB, 8 cores, 20 cores, whatever, right? So all that is to manage this, how many partitions I have, how much data I have to process. Now, when you go serverless, then all that complexity is gone. You don't need to do anything. There is no control over how many machines, how many cores, how much parallelism. Based on the data, it will automatically decide, and then it will automatically deploy the required machines, process for you, and give the output for you. But when you choose to create your own cluster to use, then at least even then you have some kind of auto scaling. You don't have to exactly decide how many machines I want. So you can roughly say, okay, start with 2 machines and go up to 8 machines. Don't go beyond that. So you can give that. So it'll work within that to upscale or downscale based on your data volume. Maybe on a daily basis, say weekends you're getting more data, or weekends you're getting less data. If you have sales transactions, sometimes weekends might be high, weekdays might be low. We don't want to change the configuration on the weekday. So what you say, put from 2 to 8 machines. So if on the weekdays less data, it might use 2 or 3 machines. Weekends there is huge data, it might go up to 7, 8 machines to process that. So that is, you use auto scaling when you configure your clusters to run. But when you go serverless, again, everything is taken care of. Whatever may the volume, it will automatically take care of how many machines it has to deploy. And again, today, to continue that, we are talking about the strategies, join strategies, because when you join, you get shuffling, data shuffling. To avoid that, so what are the join strategies that we are, what are the strategies that Spark has to it uses to go through to join the data sets when it's doing in memory, right? Does that answer your question, Srini?
Yeah, yes, sir. And one question, normally if you run any just job, okay, it will be in a buffer for some time, means just if around 2-3 people running the same kind of job, okay, hitting the same table or anything, means it will be in a buffer and it will continue to use the same shuffling mechanism.
Yes, because you're not sharing the memory between the job instances, right? It has, once you run the job, execute the job, its memory is private to that job itself. Other job can come and use your memory location, your data. Otherwise, everything will get corrupted.
Okay.
So your instance, your memory is yours. Somebody else is doing the same thing at the same time, doesn't matter. It will create its own memory for them. Okay, so whatever things you do is controlled by your job only in memory. Only your job can access that memory, not everybody. Once you write to physical location, either you write to a disk where other jobs have access folders, they can access that. Or you write to table, they can access from table. But in memory, they cannot access. Okay. It's same thing, right? Any application you run, it's not Spark. If you run any Java program or Python program, you run the same program. If two users run, they will have their own memory locations, their own variables, their own values, and their own output. No, I mean, no two programs can share the memory or access each other's memory. That's a violation. So it's a huge security issue. Okay. You good? Guys, everyone?
Yes, sir.
Yes,
Okay.
sir.
So yeah, so the whole stage code generation is what we said, where our execution or the code action that happens. Exchange is the shuffling. These are two data sets, which are like we are doing reading or generating a data frame. This exchange was, we did repartition, then we got two data frames, then we are, so after this, we are doing some more processing on the data sets. Again, there is a join, so there is a shuffle. After the shuffle of two data sets joining, here, exchange, there's some processing happening, and then again shuffle, then processing happening. Okay. So this is just representation, but remember we did our processing yesterday on one of these. So we ran this one, right? So this job, okay. So this is first data frame we are generating. This is a second data frame. Now we are doing repartition and repartition of this. One thing I wanted to show here while this is coming up, let's go. Okay, so we see here, we got the sum and we got all of these jobs triggered. We looked at this DAG yesterday. So this is the first data frame, repartition, second data frame, repartition. Then there is a shuffle here. So this shuffle is basically this repartition thing that it is showing here. This shuffle is repartition here that it is showing. And then this is expression that is whole stage code gen here. And then this is the join where we are, whole stage code gen is the some expression here. And then the shuffle query, and then whole state generation on the sum that we are doing. Okay. So this is how the DAG is generated. So just to have an idea, it's not like you have to, point to point, you have to explain what is happening at each end. But at least at a high level, you should understand how these two are correlated, how the DAG is generated, how is it related to your job, kind of a thing. So you have too many partition or joins, shuffles. So it's kind of a network issue or performance issue, basically. You have to manage. Best practice is to reduce number of shuffles by transformations. Okay. Let's see. Close this. Just want to run this again. But I didn't print the partitions here. Okay. You see here 8879. I don't know why it's not displaying on a new line, but you see the partitions, number of partitions is 8. For these two, it is generating 8 partitions by default, 8 and 8. Why is that 8?
Or is it number of cores?
Yeah. So number of parallelism, right? So maximum parallelism that you can. So it generates the multiples of the number of cores. Here we are only having this driver is 2 cores, but in the instances in the machine, we have to check. This is the 15 GB memory. Yeah, I think it is the default number of cores, default parallelism that it has. 8, so it's taking 8. But the point is, if we can do repartition 7 and repartition 9. So when I said DF3, the number of partitions now is 7, and DF4 number of partitions is 9. So you get data frame dot RDD, because RDD is the lowest level of abstraction for any data frame. That's called, we talked about it, resilient distributed data set. That's what RDD stands for. Resilient distributed data set. We know what is distributed, right? So it's like the data set is distributed across multiple nodes, multiple machines. Resilient means it can always rebuild data frame based on chaining of the operations, like we see it here. I will show you that also. When you say DF5, if DF5 is corrupted, it can always recalculate and regenerate DF5 based on the DAG or based on the chain. It says DF5 is coming from DF4. Where is DF4? DF4 is being calculated from DF3. DF3 is calculating from DF1. And then DF1 is this. So it will go back all the chain and start executing from DF1 until this DF5. Okay. Now, another thing you want to observe is where is this DF? Okay. So wherever there is only reference to that data frame, that is calculated in the DAG. Otherwise, it does not. Okay. If I don't join this, okay, then individual data frames are only calculated. But so let's say there is another data frame that I am adding here. And say DF9, okay. And it says the same, some kind of data set, DF9 is also there in this. Now, if I run, there should be another so I'm repartitioning this data frame DF10. I'm repartitioning DF9 to 5. Okay. That's all I'm doing. 1, 2, 3, 4, 5, 6 jobs are triggered. I will go back and what happened to this? Unexpected indent. See, it is. Oh, I've not displayed it. Okay. How many jobs are there? Same, right? Do you see any extra stage or extra job here for the new data frame that I added?
No, so
No.
All right. So because in the
lazy.
entire thing, yeah, there is no action on that data frame. I'm not using it. So because it is, as I said, lazy evaluation, it does not go start creating this, and creating this. It will just define and keep it. Okay. Data frame 1 is this, data frame 2 is this, data frame 9 is this. When somebody is using it, then I will generate and give it to them. Okay. For now, it just kind of keeps it in the plan. Now, when I go here, I am calculating repartition and repartition. So now it is forced to calculate DF1 and DF2. That is when it executes DF1 and DF2 and then gives it for repartition. Now, why is it, when is repartition forced? So that is an action. Now, how is it connected to the DAG here? Because I'm doing some action on the DF3 select expression. This is join. This is sum. When I do sum dot show is what it all executes. Now sum is defined on joined data frame. Joined is dependent on DF5 and DF4. So that's when it goes and looks at what is DF5, DF4. I need to calculate those two things. So DF4 is here. DF4 is again coming from DF3. So I need DF5 and DF3 to calculate. So DF4, DF3, it will go here. Let's say DF4 is coming from DF2, DF3 is coming from DF1. So it will calculate DF2, DF1. But in all of this, there is no reference to DF9. So it doesn't know when to calculate DF9 or DF10, right? So it does not do that. It's not used. So there is no point in simply generating this and again shuffling and repartitioning and doing everything and keeping ready when nobody is using it. There is no reference to this. So that's why it's called lazy evaluation. Unless there is an action which references to any of the data frames, those are not executed. It's not like sequential line by line execution. That's why we have the DAG. If it is a sequential execution, just like a Python program, it will start generating all of this line by line, executing line by line, right? So it's not execution line by line, though it is sequential, but it will only do based on the plan or DAG that it needs, and it will skip or remove it later. But let's say if I have done anything here with DF9, DF10, then once this is done, it will also go and calculate the DF9 and DF10. Okay.
So you mean at the end of the syntax, like wherever the show, then only it go to the transformations and do the action or the performance?
Yes. It's not show. It's basically any action. It can be write. You're writing to database. It can be group by, where you are shuffling the data and doing an aggregation. So any of these are actions. You can check what are the transformations and what are an actions in Spark. So transformations, all of these are transformations. Repartition, this range, add column, with column, select, all of these are transformations. Now actions are like aggregate, group by, write, display, show, collect, all of these are actions. Okay. Now let's move forward. This, when you're saying here join, right? So what kind of join? So it's an inner join, but then there are join strategies. How does Spark handle joins? Okay. So Spark has three major join strategies. It's called broadcast hash join. Then it's shuffle hash join. And then there is a shuffle sort merge join. Okay. Don't get overwhelmed by these pictures. Like yesterday, we will go step by step and we will understand. Now that we understand what is shuffle, why shuffle, what is join, we can easily understand what by the join strategies here. Now, when we look at it, when you do what is a broadcast, first we'll understand what is a broadcast for this. Broadcast means, remember yesterday we said there are multiple machines, worker nodes, right? These are the different machines. Now I'm joining two data sets. The first data set has some part of it. Let's go back here and see. Where is this? This is one. Okay. So we said these things can be on multiple nodes, partitions, right, of first data set. Similarly, second data set also will be in different partitions. Let me go here. Yeah, look at this. Okay. So I have an employee data and department data. Okay. And I'm joining these two data sets. Now, employee ID node is say, let's say machines. Okay. I have two machines and the data is there split in three machines, node 1, node 2, node 3. Okay. So on the machine 1, I have 1, 2, 3, and 4 employee IDs. On the node 2, I have 5, 6, 7, 8, node 3, 11, 12, 13, 14. I mean, this is again, they may not be exactly in sequence in each partition. They might be jumbled up also. It's not, unless you say partition by employee ID, use employee ID to do the partitions. So it will sort and then do that. Otherwise, arbitrarily, it will split the records into various partitions on different machines. Similarly, so department, we have these 4, 5, 6, 7, 9, 12, 3, 8, 13. Okay. Now, so if I want to join these two, okay, employee ID 1 to whichever department it belongs. So how do I do that? We have 1, 2, 3, 4. I think we are missing something here. This is just showing the repartition. Okay, let's do this. Let's create the example, okay? So I have employee data. So employee IDs, I have say 1 to 10, and then I have department data. So departments, I have so HR, then finance, then product, inventory. 4 departments I have. So employees, I have 1 to 10. Okay. So if you look at employee records, so it can be like 1 HR, 2 HR, 3 fin, 4 fin, 5 fin. So this, I'm just seeing which department it belongs to. Okay. Then 6 prod, 7 prod, 8 prod, 9 inventory, and 10 inventory. So I have 10 employees and 4 departments. Okay. So I want to see group by how many employees are there in each department. Okay. But I can actually get, if I have here, normally this will not be like this. This will be, you have ID and description is here. So I want to join the department ID here. So let's me take 1 here so that it will be clear. 1, 2, 2. Finance is 2. Product is 3. Okay. Does this make sense?
Yes.
This is 1 department. This is 2. This is 3. And this is 4. Now what I want to see, how many employees for department with name. Okay. So department name, if I want to have group by and department name. One second.
Hello, is it disconnected from my side or?
I'm back. Sorry. Can you hear me?
Yes, sir.
Yes, sir.
Okay. All right. So now I say this is on node 1. Okay. This can be, all this data can be on different nodes, right? Different machines. You can say node 1 or machine 1, whatever. So this is node 2. Node 2. This is again node 1. This is again node 1. So I'm just saying I have only 2 machines. So I need to anyways shuffle the data. Okay. Now, how do I join when I join this? So 1 is on node 1, HR is on node 1. So I want to get a name of this. So I want to join this with this and get the name. So this is 2, 1 again here. Okay. Now, node 3 and node 4, prod and env are on node 2. These 2 records are on node 2. These 2 are in node 1. So if there is anything, say node 1, employee ID 6, right? The department ID is 3. So where is department ID 3? Is on the node 2, right? If I want to get what is the department name for this employee, right? 6 for node, for employee ID 6, department ID is 3. So this 3, I want to join to get name. So when I want to join, this is not on this machine, on node 1. So 3 is on node 2, correct? So I have to join across 2 machines, right? You're getting my point?
Yes,
Yes,
yeah,
sir.
Yes,
because,
sir.
yeah,
So
The data
what
you need
happens?
is
Yeah. So what happens here? Now there is a data shuffle. I have to bring it onto the machine and then do a join. Similarly, there might be 10 partitions. So all the data might be here and there. So I don't want to cross join partitions everywhere, right? So I want it to be structured so that my joins are easier. So that is why I do shuffling. And then when I do join, I want to join after sorting so that all the keys are on the same machine, same partition. Not everything. So I might say 1 and 2 departments, put it on node 1, 3 and 4, put it on node 2. Okay. So this 6, 3, which is on node 1, I move it to node 3. Sorry, node 2. Okay. And 7, 3 is already on node 2. So it will remain here. Okay. 8, 3 is on node 2. 10.4 is on node 1. So I will bring 10.4 here to node 2. Okay. So see, now what is shuffled? 6.3 is shuffled. 7.3 is not shuffled because it's already on node 2. 8.3 is not shuffled. 9.4 is shuffled, right? Can I say 9.4 is shuffled? It's moved from node 1 to
Node 2. Yes.
Node
node
2.
Oh, where is 9.4? I didn't write here. Okay. Let me write here. 10.4 is also shuffled from node 1 to node 2. This here, right?
Yes.
Now, let's go here. 1, 1. This is already here. So on node 1, I'm not changing anything. So 1, 1 is here. 2, 1 is here. 3, 2. So this is on node 2, but department 2 is on node 1. So what I will do? I will shuffle this, right? So 3, 2. This is shuffled. 3, 2 is shuffled, correct? From node 2 to node 1.
Yes.
4, 2. This is on node 2. Again, this needs to be shuffled to get to node 1. So 4, 2.
Instead of doing these many times, why don't you take the departments and put in the employees?
Exactly. You are coming to the point. Okay. We will get there. We will get there. Just hold on for a thought. We will talk about it. Okay. Now, for 2, then 5, 2 is already on node 1. So there is no shuffling. Now, everything is done. Now, is it easier now to join? See, 1, 1, 2, 2. All of these, I just have to join 1 and 2. Both are on node 1. 3 and 4, I have to join. Both are on node 2. So this join happens within node 1. This join happens within node 2, right? There is no join now happening across 2 nodes. I have shuffled the data so that the keys coexist in the same machine so that it is easier to join. Okay. Now this is because you're saying employees might be, say, up to 1,000 to 10,000 or 100,000. Departments might be, say, 10, maximum, some say 10 to 20, right? So looking at this, this is which one, what do you see here based on the data set volumes? Which ones?
There's a huge difference.
Yeah, there's a huge difference. There's a huge big data set. This is a smaller data set, right? So there's one big data set, one small data set we are joining. Even if it is smaller data set, because I have 100,000, so data is spread across all the nodes. This department data will also be spread across all the nodes. So I have to respectively shuffle all of that data. Instead of that, what I do is take this 10 records or 20 records and take a copy and send it to all the nodes. Okay. So let's say I have from node 1, I am processing all 100,000 records. And then let's say I have 8 machines. And in 8 machines, I have this 100,000 records, 1,000,000 records, or whatever. Now, departments are only, let's say, 20. So what I can do, instead of shuffling the data around all 8 nodes, I will just take this 20 records and stick it, copy and paste in all the machines, right? It's a smaller data set, right? It doesn't make any difference. If I have 1,000,000 records and spread across 8 nodes, which is say 100,000 or 10,000 records here, if I just add 10 records or 20 records, it doesn't make any difference, right?
Yes, sir.
So I'm copying and broadcasting this data set to all the nodes. So each node will have a copy of the entire data set because it's a smaller data set. Now, there are some limitations. What is the size of the data set? What do you call small? What do you call big? Okay, I think there is one less than 1 GB or something you call small data set, fit for broadcast. So there is a configuration you can set. Consider this size for broadcast hash join limit. If it is less than this, you broadcast. Okay, consider this join. Don't go for other type of joins. Second thing to remember is the entire data set has to fit in the memory of these nodes. Okay, if it is this you're saying 1 GB, the smaller data set itself, let's say, is 1 GB, and this is say 100 GB or whatever. But this 100 GB is partitioned, right? So it can be on, say, let's say 16. Okay. Let's say this is 16 GB. Now I have partitioned. So each node will have 2 GB of this data set. Okay. Employee data set. Each node will have 2 GB. Right. Okay. And let's say department is, 1 GB. Now you're copying this 1 GB data onto all the nodes. Now total, this is 3 GB now. So if my node, this here is only 2 GB machine, it can only fit this 2 GB. Of course, there will be some overhead and all of that. So even let's say 3 GB. My node 1 is 3 GB RAM. 2 GB is taken by this data set. And if I put 1 GB in there, what is left for processing, OS, memory, overheads, all of that? There is another half GB that goes. So we need 3.5 GB at least to fit the entire data set here, but it is only 3 GB. So you get out of memory error. It's trying to fit this into the memory where you don't have enough memory. So you have to see whether your machines have enough memory to put the complete data set into this. So most of the times it should be possible. We'll consider smaller data sets. So what we are doing, we are broadcasting, sending the entire data set to each of the nodes, so that now any department you're going to search will be here only. You don't need to go to any other node. So all this join happen here, all the join happen here, all the joins, it is called within the node. Now you have avoided the complete shuffling by doing a broadcast. There is no shuffle, right? There is no data shuffle. Correct?
Yes, sir.
Now you can just go and join all of these and then take the data and combine it. That's it. So you have avoided the shuffle of 2 GB across 8 nodes. God knows how many times it has to go through the entire network to figure out which department keys it has to put on which node, how many records it has to push to each node to make sure all those keys are coexisting. So all of that processing complexity is removed because you broadcast as the smaller data set, right? So that's exactly same thing here happening. You have 4 worker nodes. There is a small data frame like department. And then you are sending that small DF copy to each worker node. So this small DF here, you're sending the copy, 4 copies to 4 machines. The large DF, see, large DF is not completely on this machine. You can see here partition. So one part of the larger data frame is here, one part is here, one part is here, one part is here. So this entire departments will join with whatever employees you have here, 1,000 or 2,000. This department copy will join with employees here, maybe 5,000, 10,000 employees. Same thing here, same thing here. It's a hash join. It's simpler. There is no shuffling here. See? Can you see this? There is no shuffling. Okay, parallelism is maintained. You understand this?
Yes, sir.
Awesome. Okay. So this is the broadcast join. Now, shuffle hash join. So basically, it's the normal. If we don't do a broadcast, what happens? Right? So this is a worker 0, worker 1, worker 3, 4. It's just representing what we talked about. Chunk of data of relation 1, chunk of data of relation 2. So it's kind of based on join keys, it's shuffling the data around all the workers. Okay. So similar keys having here join key equal to 1. So where the worker, employee and department having same keys, same department keys will be here. Similarly, another part of the employee's data having, let's say this is department 1, all department 1 data, all employees with department 1 are moved here, all employees with department 2 are moved here, all employees with department 3 are moved here, all employees with department 4 are moved here. This is when we are saying not department. Maybe let's say a different. You can talk about what you call transactions, transaction data. Okay. You want to join customer with address, for example. Customers might be huge, addresses may also be huge. Both are huge data sets. You cannot send all the addresses to a customer. You cannot send the entire data set of the address to all machines. You cannot send the entire data set of customers to all the machines, right? So both are huge. So both will have partitions on multiple machines. But you say customer having similar address ID, some address, will be on this machine. Some customers having similar IDs will be on this machine. Basically, you're shuffling the data around, and then you are joining on each worker. So that is your shuffle hash join. Another strategy is shuffle but sort merge join. So instead of moving all the data around trying to figure out, what it will do is it will first sort based on the join key. For example, addresses and customer. So it will sort on the address ID. Address maybe say each state. Okay. And then it decides all the customers having the address in these states will form one partition, will go to this machine. Okay. Or something like that, by ID or by state or by something, it will sort so that it is easier to make the chunks into multiple machines. And then join will be easier. Okay. So instead of 4, 1, 3 here, it will sort 1, 3, 4. 6, 4, 2, 1, it will sort this ID. And then it is easier to merge. ID 1, 3 is not there. 4, 1, 4. It will join here. So basically, there is a sort step before the join in the merge. So these are the three major or join strategies that Spark uses to join the data sets. So this is the important one from the perspective of interviews, right? You have to talk about, you can do a suggestion to join to use broadcast. You can force the Spark to use, hey, use broadcast join. I know my data set is smaller when I'm joining, use this data set. So this is default default, I think, shuffle, sort, merge, join. So this is the default, because remember when we saw this, where is that? Not this one, not this one. Yeah, so here on, right? Is this the one we looked at? No, 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 no. Yeah. See here, before the join, you see the sort, right? Guys, come on, acknowledge. Are you there?
Yes, Arun.
Okay. So when you are doing after shuffle, then there is a sort. Then
Before
there is
join, yes.
join. Okay. So this is the shuffle, sort, merge, join. Okay. Now let's get into action.
But we did not ask it to do the shuffle sort, right?
Yes, we did not. It's default. It knows. It has some intelligence, right?
Okay.
Okay. That's what we want. We want it to be more intelligent to decide. Where is this? Yeah, let's go to join strategies. Let's check this. It's done. Okay. So I'm taking the example of movies. I have the file here. I'm reading the file. This is all normal, regular Spark jobs. There's nothing complex. We're just reading it. So you don't see any complex thing here. There are no stages. See here, it's just only one flat scan CSV read. There is nothing, no exchange, no shuffle, no join, nothing. So correct, simple that. Now I come here, do the same for ratings file. So the first I have written, first I have read the, which file is the movies? Then I read the ratings, right? So I can join movies and ratings, right? What is the join? Join the ratings with movies data frame, movie ID, inner join. Okay. Now I run this. Once it joins, I am asking it to explain the data frame join. How you are joining it, please explain what you are doing. For people who are already done SQL in Oracle, right? Yesterday we were talking about, we have the explain plan, right? Subbu, Murali, Srini.
Yes,
Yes, sir.
sir.
Explain plan, right? So same thing, explain plan. Here it shows your physical plan. See here, what is it using? Broadcast hash join, right? Because it found one of the data set to be smaller. So it has broadcasted that. Movies is the smaller one. Ratings is the bigger one. Okay. So what it has done, it has done a broadcast hash join to, movies to the ratings. So broadcast hash join with the movie ID.
So Arun, so we no need to mention which join, right? So the system, the machine it will take.
Yeah, sometimes it does. That's what I said. It is intelligent enough to decide if something is smaller, it will. But if you think it is not smaller, hey, don't keep pushing all that into the network. I don't have enough memory. You can force it. Sometimes it can go wrong. Sometimes you can change and force it. Don't use the broadcast hash join. It's kind of a fight. Sometimes it says, oh no, you are not smarter than me. I will still use this.
So force it means we need to give some command. I mean,
Yeah. So you can not command. Remember hints in SQL.
yes.
Yes. So same thing you can do. You can give a hint. Okay. Let's say I'm doing again movies. Movies data frame count. What is the movie data frame count here? So what I'm doing here is I'm taking a copy of the same movies. So both are now same. Huge. I want two huge data sets. If I take the same copy of it, so then both are same, right? So that is not one bigger, one smaller. Both are same size. 722447. I'm taking this copy. I took a copy of the file and then I created another data frame from that copy, which is like movies copy data frame. So now both my data frames have the same data. So if I think we should have done this display. Let me rerun this. Vikas, Shanmuga, are you guys following?
Yes, sir.
Yes, sir.
Awesome. Okay. See,
Now we
now
are trying to join the data.
yeah. So now we are joining the same data set with the same size. I mean, basically both are same movies only. They will have same IDs. Okay. Now here I am setting some configuration. Prefer sort merge join false. Okay. Sort merge join, as I said, is the favorite for Spark. It does this default. Okay, I know this is your favorite, but don't do it. And then I said movies copy data frame dot hint. I am giving a hint. Hey, use shuffle hash join. Don't use sort merge join. Use shuffle hash join. So if I go here, this is my shuffle hash join, which means I don't want sorting anything. I just want, go haywire, do all that, moving, shuffling across data. So I put that hint, shuffle hash, again, join with ID, inner join. Both have same ID, so it's inner join. And then display join.df and explain. So I'm saying join it and show me what you are doing for the join. Explain your join to. See how much time it's taking to do the join. It is joining 800K records with again 800K records, right? 34 seconds it is taken. And look at the join here. What is a shuffle hash join? Cool.
Yes, sir.
So we asked it to use shuffle hash join. It has used shuffle hash join. Okay. And then there is a lot of exchange, hash partitioning, exchange here, a lot of all that processing that goes on. Now, reset that configuration, prefer sort merge join to true. And now I am using the same data sets to join with now hint as merge, which is like sort merge join.
Sort.
That is default. You don't have to give, but sometimes it's
Oh,
good.
so much faster.
Yeah. See, only 14 seconds. You're getting a hang of it now, right? There is a reason why it is smart. It chooses sort merge join because it knows that is faster. Sort merge join. Okay. So these are the different strategies, join strategies that Spark follows. Now, when we are doing, so we see how we are connecting things. Okay. We started with Spark internals. We went into that. Then we said there are multiple stages. Why is a new stage coming? Every time there is a new stage, or we say that if there is a new stage, it means that there is a shuffle.
Change.
Whenever there is a shuffle, data shuffling, then you get a new stage. Now, why does shuffle happen? Then we connected it to the joins. Now we explained how joins happen, how it needs to join. So to join the same set of data, it needs to shuffle because data is there in all partitions. So it has to co-locate, coexist the data keys. So it shuffles, or when you do repartition, it shuffles, or when we do group by, it shuffles. So then we connected the shuffle to the joins. And when we came to joins, now we are connecting the joins to what are the join strategies that uses to join when it decides which join to use, which shuffle to use. Is there a shuffle or not when it does these joins, right? So that's how we connected to the strategies. Here. Okay. Simple broadcast join. Exchange is just the broadcasting. This is the full scan CSV file that we have broadcasted. And then within this, within the same stage, it's joining. Just sending this data set and then joining everything here. We have just two tables, and then everything is here. This is scan, this is query shuffle. We read the other data frame and then copied here, and then this is joining. This is broadcast. So you can go ahead and check the other ones. Copy. Yeah, let's go here. Let's see what this has done. See, there is an in-memory table scan. Okay, this is the first one. This is the second one. Exchange, both here, shuffling, and then join. And while we are here, remember the green dot. Okay, we will come back to this green dots later. Can anybody guess what the green dot is? Anyone? Green. It says here, in memory.
Is it
Yes, it's a sort.
reading or
So,
It's cache.
She,
yeah.
So we are caching this. 1 second.
That is only in two places.
Yeah, sorry. What is it, Subbu?
Yes, Arun. Yeah, what I'm doing. That is only in two places.
So this is one data frame that we are caching,
And next,
another data frame that we are caching.
okay.
So this is this data frame, this is this data frame. Okay, we'll go there. So that's why I'm showing you here. We're connecting things. So how the cache, how does the cache help? Okay, though it is in memory, we're saying Spark processes everything in memory, then why cache? So even in the in memory, how does cache help is what we are trying to see. We will explore next from here. But this is good, right? You have done the Spark join strategies. Shuffle hash and this is sort merge. So see here, there is a sort. In the previous DAG, you didn't see the sort, right?
Yes.
Observe this, yeah. So in the sort merge join, there is a sort step before the join. In the shuffle join, there is no sort, it's just direct. And of course, broadcast, we know there is a copy of the data into all the machines. So these are the three different strategies. So the default is shuffle, sort, merge, join. That's the default. Now, we talked about the green dots, right? So let's go there, check how the caching helps. Okay. So we all know what caching is, right? So we calculate something, we keep it in memory, and then we reuse it. That's simple, cache. Now, Spark also has caching mechanism. What type of cache it has? So there are different levels, even in the cache, persist. There is memory only, which says once you calculate, keep everything in the memory. Okay. Serialization is just another format. You serialize and deserialize the data before putting onto memory. We'll come to it. Memory and disk, which means when you calculate results, you store it in memory and disk. So if it doesn't fit in the memory, you spill it onto the disk. So some part will be in memory, some part will be on the disk, whatever does not fit in memory. Disk only, don't put anything in memory. Whatever you calculate, keep it to the disk and read it from the disk. Serialization, memory only, but serialize it before you write and deserialize it when you read. Memory and disk, serialization, same. Put some in memory. If it doesn't fit, go put it on the disk, the remaining part of it. But before writing, serialize it. And when you are reading, deserialize it. Okay. How does these things impact? What is the best in this? It all depends on your network IO. Okay. Memory only, I have lot of memory. You calculate, you store in memory and reuse it. Don't calculate every time. Remember the green dots. Memory only serialization. This will help with reducing the size, right? I'm putting it in memory, but serialize and deserialize. So it's like encryption or serialization. It will reduce the amount of data or size of the data that you are storing in memory. But what is the downside of it? What is the overhead? How much time it takes
One
to,
more step.
yeah, one more step. How much time it takes you to serialize and deserialize. That is your added IO or added processing. You are reducing the memory footprint, but you are adding a bit of processing IO. So if you think processing IO is very less compared to the benefit I get putting it everything into memory, use that. Now memory and disk is same thing. So if I have 2 GB memory left and what I calculated my data frames are 4 GB, I cannot store it. So I'll say memory and disk, 2 GB it stores in the memory, 2 GB it stores in the disk. When you read back, it reads 2 GB from memory and 2 GB from disk. Again, it's not ideal, but still, given whatever we have to use it. So at least 2 GB I can read faster from memory, and the remaining 2 GB anyways I will read from disk. Even from reading from memory and disk, it still is faster for me rather than going and calculating the 4 GB data again whenever I read it, I process it. If I'm reading it or accessing the data frame 10 times and I'm calculating the 4 GB 10 times, 40 GB, that data I'm again and again processing. There is compute, there is cost, right? And there is processing time. So even considering all of that, I'm still okay writing to disk and memory and reading it back. Same thing with serialization. Now I'm writing to memory, writing to disk, and I'm serializing it before writing and deserializing it before reading. Still, I'm good. Even then, I'm still saving on cost and time instead of recalculating the data frame again. The final one, disk only. Again, it's okay. I don't want to calculate, but I don't have memory. But once you calculate, write to disk and read from disk, that's fine. That's faster than calculating. So use the disk. I have a lot of disk space, use it. So it's IO, a lot of network IO that you read and write from the disk. But still, it's kind of a caching. So you're not calculating, but you're reading already calculated data frame. Got it? These are the options that you get to do the caching. Guys, are you with me? Clear?
Yes, sir.
Yes, sir.
Got it.
Okay. Now, let's go back here. So I'm reading this file, all of these files, Amazon files. So we had so many files in this, right? Remember Amazon data set that we processed all transactions. We have huge files. You want to see
Yes,
how
sir.
many files we have? Okay. So it's just Reddit. There is no processing. So I run this. I'm calculating this. This took 20 seconds. And I'm doing this df select. df2 is dependent on df1 dot filter. See, again, it is not doing anything, execution, because there is no action, right? These are all transformations. Understand? That is why it's saying 1 second. It's not that it has already done in less than a second. It's just saying, okay, I executed. Now I know what to do. Transformation only. This is transformation only. This is transformation only. This is transformation only. This is transformation only. Here comes the action. Okay. Now, display df3.count. Now it has started execution. Where is df3? df3 is this. See, I have given you the chain here. Follow this. df3 is dependent on df2, right? Where is df3? df3. So if I want df3, it is dependent on df2. Do I have df2? No. So I go and calculate df2 first. What is df2? df2 is dependent on df1. Do I have df1? No. So I go and calculate df1. So what is df1? df dot select, right? So that is df. What is df? df is spark dot read. Now I go and read the CSV file and do all of this chain of transformations to get the df3.count. So to get the data frame 3. Similarly, if we access df4, if we access df5, what happens? So df3 is dependent on df2. And again, same. df4 is also dependent on df2, df1, df spark rate, right? So what is DF4 is again also dependent on DF2. DF5 is also again dependent on DF2. Correct? All of them are same data frames. Now, when we say I have already done it, DF2 is already there. Now give me DF4. It doesn't give you. It's again started calculating DF2. Again, it is going to DF1. Again, it's going to DF. Again, it's going to Spark. This is how the DAG, right? It knows the DAG. It knows what to calculate, and it will start calculating.
So if we cache it, it won't calculate again.
Yeah, we'll get there. We'll see. Okay. See here, all of this exchange calculations. Whole stage code gen calculation. If we go, so this took 17 seconds. Okay. This took 15 or 16 seconds. Again, if we go here, see there are no green dots anywhere. Okay. So it's all, there is no caching, no memory, everything it's doing recalculation. So this took 12 seconds, DF5. If I calculate DF5 again it goes through all this calculation of all the stages, basically all the data frames. So 13 seconds, I go here, again, all of this, same thing, transformations it does and calculates. 13, 15, 17 seconds, almost close, right? Now I go here and do a data frame 2.cache. So I'm caching the data frame 2, which is this, right? So DF2 is calculated on all of these, basically. So when I do a DF2.cache, it calculates the data frame 2, right?
That's supposed to be Olivia Rodrigo. No, that's how it was. Yeah, you can tell somebody easily. You know what? I don't even know what that computer looks like. So it could be either. I'll just say look like because that's the way.
Okay. 16 seconds. Again, it does the entire processing from DF2. And now you see the green dot here, right?
Yeah.
Now this is cached in memory table scan. 16 seconds. Now I will go back and say, give me df4.count. See, now it is less than 1 second. df4.count, when we did here, what happened? 15 seconds. df4.count, now less than 1 second. Now if I go here, I will see the blue dot. So it's not processing everything. It's just going and reading from the cache. I do df5 again less than 1 second. This is going and reading from the cache. From 17, 15 seconds, 16 seconds, it came down to less than 1 second. Since it is not doing the calculations again, it's just using the cache that it has here. Right?
Yes, sir. Yeah.
df3.count, same thing. So here, as I said, these are all the options. So you can use df2.persist. Cache is like, memory only default. You can also use persist. So all of the ones I have shown you options, get those options when you use this persist. With persist, you get options. With cache, it's the same thing, but it's default memory only. So persist, you can use memory and disk only, serialization, all of this. Okay. If I have 10 GB of data and then say I have only 5 GB memory, if I use just memory, you will get memory error because 10 GB cannot fit into 5 GB. If I use memory and disk, I will store, it stores 5 GB in the memory and the rest 5 GB to the disk. If I use disk only, it will write the entire 10 GB to the disk. That's what we talked about, we went through. Now, once I am done with it, I don't want to do any of the caching. So I don't want to use anymore. So I can remove it from the cache. So I just say unpersist.
You weren't gonna give it a top because honestly, this should be a huge waste of time. That's not true. Come on. I mean, just look. You could make it roll and push it out of a boat in the middle of the ocean. Pretty sure that's possible. Yeah, exactly. These are gonna be more given in the top. That's different. They're low numbers of this one. These days, this is not real popular. They're like this high. We're trying out loud. He was born in Madison, Wisconsin.
Srini, can you mute? I think we are hearing some. Okay. So I have unpersisted it now. So DF2 will not be there. Okay. Now, if I go and do any of this, now you don't get, because it's not there in the memory. Now it is going back and doing all the calculations again. It has to do. So again, it will go and take 15, 17 seconds, 13 seconds, right? Now you understand the concept of cache?
Yes, sir.
Awesome. So I think those are the two things that we wanted to discuss to wrap up. There is one more thing. Just give me 1 second. Probably I'll briefly touch upon that. And then wrap up. Okay, my laptop charging. 1 second. What's happening? It's not charging.
So Arun, so this cache, so whenever if you want to make it fast or something, so we can use it, right? Depends on the scenario.
Sorry.
No, this cache. So whenever if you want to use some calculations or something, I want to make it fast, so we can use the cache, right?
Yes, definitely.
So we need to mention. We need to mention that cache, the type and everything. It's not like the system it will take and do it with the AI, something like that.
No, caching, yes, you have to add yourself. But again, when you are doing DLT pipelines, it is all automatically taken care of. AI. Yes, because of serverless, it knows where to cache, when to cache, it will automatically take care of all of that. Okay.
Okay,
Now,
only for the DLT.
yeah. So I think it will come to all as and when. So this is good to know. You can verify when you are doing if it is caching or not caching. You look at the DAG, you will know. But you can add your own caching. Yes. Okay.
Okay. Yeah.
So understand the concepts. Yes, you can say, yes, I will add it. When you ask, I will see the performance. If Spark is not doing by default, then I will add it explicitly. Right? Sometimes it does not understand. Then I will add, I'll give hints. Why is there hint? Because if the system is intelligent, it will already take. If it is not intelligent enough, I want to force, I give a hint. Right? So that's how it is. You can say that. I will run it. If it deducts automatically, it knows processing is good. If caching is done, that is fine. If not, I will add my own explicit caching for that. So this is all what happens in the adaptive query execution when you run, right? You're seeing that explained plan. So SQL query or data frame, it goes through this entire process. It's called adaptive query execution. There is a logical plan. It does analysis. It's unresolved. Then you get a logical plan. It does optimization, which is like optimized logical plan. Then it does a physical plan. It gets multiple plans. Then it goes through the cost model for each of these physical plan. And then it will choose which model is better. Then select that physical plan. And then it's done the code generation. So this is the entire process that goes through when it does the query execution. Now, when we are doing this, there are a lot of performance improvements that were done, which added speeding up the Spark SQL with using adaptive query execution. So what it does, AQ framework, all of things that we have discussed right now, right? It does dynamically. Normally, when you choose a plan, it will go ahead and execute it. But in the adaptive query execution framework, first it kicks off all the stages that are not dependent. And then based on at each intermediate stage, it will reevaluate the plan and see, okay, I have chosen this. Is this still good? A good example I can give you is, we started with, say, 2 huge data sets. Okay. Employees, movies and ratings, for example. Let's say both are huge data sets. Now we have decided to go with shuffle, sort, merge, join. Somewhere down the lane, I filtered out one data set saying, select only for the current year. Now the data set has drastically reduced based on the execution, that on the year, right? So movies were like 700, or 20,000, 30,000, suddenly became, say, 1,000. Now I don't need to go to sort, merge, shuffle, join. This is a smaller data set. I can switch to broadcast join. So that kind of intelligence is built in the adaptive query execution. Okay. So it can dynamically coalesce shuffle partitions, which means, so there are, say, 100 partitions and 30 of them are empty. But when I'm still shuffling, I have to shuffle all the partitions, or some partitions are huge, some partitions are very small. So one partition has 1,000 records, one partition has 10 records. I can just merge those two and make one partition, 1,010 records. So that when I'm joining, I can completely ignore one partition or remove that partition, so that my overhead is lost, overhead is reduced. Because for each partition, then I have to have a task, I have to check and join and see there is no data, so don't need to join. Or there are 10 records, I need to join those 10 records here and 1,000 records here. So you can dynamically reduce, coalescence, reduce the shuffle partitions if it is not required. Reduce the number of partitions so that when you shuffle the data, it will be less, right? So shuffling across 10 buckets is harder, right? Shuffling across 2 buckets is easier than shuffling across 10 buckets. Then dynamically switching join strategies. That's what I talked about. Based on the intermediate results, it can reevaluate and switch the strategies from shuffle, sort, merge, join to broadcast join if it fits better based on the intermediate results or the new data set that has come after the transformations that we apply. Optimizing skew joins. Again, we talked about this. If one partition is too heavy, a lot of data is on that machine has a lot of work to do. That task is taking too long to complete. So those kind of skew joins, it will automatically detect and reshuffle the partitions so that it will take care of, reduce the inequality and total time to completion. So dynamically coalescing shuffle partitions. If there are too few partitions, data size of each partition may be very large. If it is just, as I said again, let's say 100 partitions versus 10 partitions. If it is just 10 partitions, data size of each partition may be too huge. And then we may need to spill data to the disk. Again, it will increase the IO, right? So I have to spill to the disk, read back from the disk and all of that. If there are too many partitions, like 100 partitions, data might be small, but I have to go to each partition and then do. There is a lot of network data fetches that is happening. That is again inefficient. So from 10 to 100, maybe I can find a middle ground, say 50 or 40 partitions. That is ideal, right? So this is all the without adaptive query execution. So you have all these 5 partitions here. These are 3 small, these are 2 big. Now after AQE, what it will do, it will reduce 3 partitions. So these combine all of 3 into 1. So now they are all equal partitions. Dynamically switching, again, we're talking about here, sort, merge, join. He also used the same example. Sort, shuffle, filter, scan. Now re-optimize this, broadcast, shuffle, filter, scan, and then join. Okay. So from static cost 15 M to actual, it came to 8 MB. So that is dynamically switching the join strategy. Same thing, dynamically optimizing skew joins. As I said, some partition is becoming very large, the others are small. So all of this becomes network IO, shuffling data, and this may take too long to complete. So with AQE, now it will split this one into 2. So you have more partitions now, but the time taken will be same, parallel. So this will come into this. So it can automatically switch dynamically. So these are the 3 advantages that you get with adaptive query execution that was introduced, from I think Spark 3. It is default. I mean, you don't have to do anything. It is it comes automatically. Spark 3.0 is shipped with the AQE framework. So all of this happens by default. This is something to know. We'll copy this, just do a reading, nothing to go deeper and understand. Just you need to talk about it. Whatever I'm talking right now, yesterday and today, if you go through it multiple times, understand, practice talking these topics, throwing around these fancy terms, and then being able to support when there is a question on those terms. It will help you very, very much in your interviews, in your discussions. That's all. That's where you can showcase you have so much of understanding and knowledge of how actually Spark works, how Databricks, Spark internals or Spark distributed processing or Spark processing works. So yesterday's and today's, I think that will give you a very strong foundation and confidence. Okay. Let me, where is this? And always know how to get this chat. This is the chat. No, this is not the chat. Where is this? Oh, here. Okay, that's regarding the AQE. You can go through. Okay. All right. So I think that's all I have. Any questions about yesterday or today, the concepts? With this, we wrap up the Spark internals. And then we'll have 2 more weeks and to talk about. So as I said yesterday, so next week we'll talk about Unity Catalog, Hive Metastore, and some of those stuff. And the last week we'll talk about certifications. Last week will be mostly you guys. talking about the certifications and material and questions you can discuss. It will be open forum. So next week is likely from my end doing more hands-on or practice or explanation. After that, it's you guys, you have to start doing the last week. Today I will update the links for certifications in the same document that we are uploading these things, videos. In the end, I will add certification links that you can follow. Anything else? All good?
Yes, sir.
Okay. All right. Have a good day. Have a nice rest of the weekend. I will post it. Please go through these videos. Very important from the perspective of interviews, from the perspective of practicing. So specifically these things, not many people know. I can tell you confidently. People can go through videos, can run some few things, but they really don't understand what these concepts are. So be comfortable with this and practice. You should be good. Okay.
Okay.
All
Thank you.
right.
Thanks for
Have a good day.
Yeah, thanks, Arun. Thank you.
We'll meet again.
Thank you.
Keep practicing. All right. Take care. Bye.
Yeah, thank you. Bye.